Hello, I am Mengqiang Chen, and the topic of my presentation is standard deviation-based adaptive gradient compression for distributed deep learning. There are 4 parts in this presentation. The first one is background and related work. Now, with the increasing size of data and training models, distributed deep learning as an effective way to deal with large-scale model training. However, distributed deep learning usually requires frequent exchange of gradients data during training, which leads to communication bottlenecks during the training process. Therefore, the researchers proposed the gradient compression technique, thus relieving the communication pressure between the nodes. Depending on the compression methods, gradient compression can be divided into gradient quantization and gradient specification. Gradient quantization qualifies gradient data by reducing the precision of the gradient values, while quantify the gradient data in a small number of bits. Gradient specification reduces the communication overhead by sending only part of the gradient data. The main work of this paper consists of the following 4 points. The first one is design the standard deviation-based threshold mechanism for filtering gradients and reducing the communication overhead. The second one is design adaptive learning rate revision according to the change of the training accuracy. The third one is design momentum compensation to solve the problem of missing momentum in synchronous parallel training. Finally, evaluate the SDAGC and experimental results show that our solution performs better. Then is our optimization algorithm design. The optimization algorithm consists of 4 parts. The first one is standard deviation-based threshold mechanism. The second one is residual gradient accumulation and local gradient clipping. The third one is adaptive learning rate revision. The first one is momentum compensation. The standard deviation represents the dispersion of gradients. A small SD indicates the little difference between gradients, and most of them are stable and equally important. If SD is large, only large gradients will be sent, and the smaller ones are kept as regular to the next iteration. The key idea of this method is to select a dynamic and reasonable gradients dropping threshold by computing the standard deviation of gradients. This is algorithm execution flow. The residual gradient accumulation algorithm properly handles the residual gradients after gradient compressions, reducing the loss of parameter update content and further ensure the proper convergence of the work. The local gradient clipping algorithm, on the other hand, solves the gradient exploration problem encountered during LSTM model training and avoid the adverse effects of anomalous data on model. To reduce the impact of the gradient compression algorithm on the rate of convergence, and to improve the speed and stability of the model convergence. In this paper, the learning rate adaptive adjustment algorithm is designed so that the learning rate can effectively respond to iterative training at each stage of the model. The algorithm closely follows the variation in model accuracy and uses accuracy as an observable indicator of the adaptive adjustment of the learning rate. In the distributed synchronized parallel training, the parameters of the momentum SGD optimization algorithm are updated as shown in Formula 1 and 2. In the distributed training without data compression, Assuming the model needs to undergo successive iterations of training before the next parameter update, the actual update formula for the parameter Wi is shown in Formula 3. When the specification compression algorithm is used, the formula for updating the parameters of the algorithm is shown in Formula 4, 5, and 6. That is, only some of the parameters can be updated after each training iteration, and most of the parameters are delayed due to the data compression. For example, the actual update content of the parameter Wi after t iterations of training is shown in Formula 7. Compared to update Formula 3 without data compression, each gradient is missing the corresponding cumulative momentum vector product. This paper compared parameter update formulas and find that currently only those gradients that act immediately on parameter updates are able to obtain cumulative momentum factors. Whenever in the training of specification compression algorithms, gradient data usually needs to pass some accumulation before acting together to update parameters. In practice, however, this part of the gradient is also supposed to participate in the momentum calculation over the cumulative period to obtain the cumulative momentum factor product. Therefore, this paper proposed a momentum SGD compensation algorithm that allows those local gradients that don't have a local gradient that can act immediately on parameter update to also participate in momentum calculation to obtain the cumulative momentum factor product and achieve momentum compensation. Then is experiment and performance evaluation. In this paper, the Tianhe-2 GPU partition and PyTorch are chosen as the hardware and software platforms for the experiments. The SDA-GC was tested using 3 different types of training models and data sets. In this experiment, 3 general comparison algorithms and 2 specific comparison algorithms are used. In the hyperparameter selection section, 4 different alpha values are initially selected to test their threshold screen specificity and training accuracy during the training process. From the experimental results, it can be seen that a good balance between specificity and accuracy can be obtained when the alpha is chosen as the primary size of E. From the experimental results, it is known that the learning rate adaptive adjustment algorithm can effectively improve the convergence stability, speed, and accuracy of the model convergence, and the momentum SGD compensation algorithm also effectively solve the problem of missing momentum and improve the convergence accuracy of the model. In the image classification, SDA-GC effectively improved the compression efficiency of the specification compression algorithm and achieved higher compression ratios in both shallow and deep neural networks and residual networks. The accuracy is also relatively similar to baseline. SDA-GC also consistently achieved higher compression ratio and better model convergence in training environment with different number of computational nodes. The experiment result of the communication time, percentage, and acceleration performance are shown in the table. It can be seen that all data compression algorithms are effective in reducing the communication time percentage. with SDAGC obtaining the lowest communication time percentage. Compared to baseline, it achieves 3 times the acceleration ratio, effectively reducing the time required to training the model. SDAGC is also able to obtain better accuracy and enters most convergence physics as far as possible while maintaining the stability of convergence under large scheduled dataset. In the language model, SDAGC achieved the lowest degree of confusion and the best compression ratio in the specification compression algorithm for comparison. Baseline consistent product the best convergence result during the experiment, while SDAGC had significant fluctuations in the early stages, but eventually were also able to converge quickly and approximate the baseline curve. In the speech recognition, SDAGC obtained the lowest word error rate and the highest compression ratio. And there are no large fluctuations through the training process, and the model converges smoothly. Finally is the conclusion and future work. We will design a novel approach to reduce the communication overhead between workers while keeping model performance not affect much. Evaluate the performance of SDAGC using various machine learning tests, image classification, language modeling, and speech recognition. SDAGC can be used in asynchronous parallel and experiment with more GPU nodes and large schedule models and data sets. That's all. Thank you.